Hello my friends, welcome again to my video channel. Today we will continue with the TR7, which has a faulty PA. We've identified the problem, faulty final transistors. We also had some burned resistors. Explanation was in the last video. What happened? Now the new transistors arrived. You can imagine what it costs. Not cheap, including postage and custom fees and so on. Okay, let's don't talk about it. I promised you in the last video to open the bad one of the bad transistors, and to have a look into it. It is already prepared, so let's have a look onto the screen. Here you will see the arrangement with the microscope. It's a cheap one, not so expensive. I think 15 euros or so. At the screen on the laptop, and now we can focus on the picture. This is the internal view. Here we have the base connection on this side. This is a collector. We have here the cut tab, and these two sides here are the emitter connections. There are two emitters, and we see here a lot of bonded wires. I try to increase it. Let me say, oops. We can see some of the bonded wires are a little bit damaged, but this happened when you see this and this, here this wire, but this happened when I opened the case. I was not careful enough. I thought it is more robust, the case. It's only we can see it here, it's only a small ceramic cap. It's like a cup, and the top cover is rather thin. I thought it's a little bit more robust, but suddenly I broke through and I touched the wires here, the bonded wires. Okay, just for information how it looks like, it's a very sophisticated transistor, and it is surprising that that the collector and base are connected with such thin bonded wires. Only where the damage is, I don't know. Obviously inside maybe one of these transistors. There's a lot of transistors which are connected in parallel. 1, 2, 3, 4, 5, 6, 7, 8. I count 9. Do you have 1, 2, 3, 4, 5, 6, 7? I count only 8. Okay, maybe 8 base connections and 9 collector bonded wires. Well, that's it. The new are here, and now we can start repairing the PA. The two burned resistors are out. The new ones are in. This is the 10 ohm resistor, brown, black, black. And this is a 2 ohm resistor, red, black, black, and silver. Same as we have here. The third one, the 100 ohm resistor, was okay because this resistor has this choke in series and it couldn't be damaged. Now next step is to bring it back, renew the grease where necessary, and then install the new power transistors. The board is in place again. All transistors are mounted with isolation pads where necessary. This transistor is not isolated. The thermal grease is renewed everywhere. Do not use too much thermal grease, makes no sense. Thermal grease is only there to squeeze out the air, not more. Thermal grease is a worse thermal conductor than metal. So keep it as thick as necessary, but as thin as possible. Only a very small layer, it is completely sufficient. So the transistor gets thermal contact to the metal without air between, but the thermal grease itself should be very, very few, only little volume, not more. Later when we install the power transistors, we also have to clean this surface here. There's some stain or so I see, and add some thermal grease, but only a very small drop, not more. Well, these transistors are specified with a HFE of 80. It's also here tested 80. I will use this transistor tester to see whether they are really symmetrical and what this says regarding HFE. The first transistor is connected. Yellow is a base. 3. Number 2, the black one, is emitter. And number 1 is red, it's a collector. Now let's start with the test, what it says. Remember, test was 80, according to the supplier. HFE of 68. 1 is collector, red one is a collector, that's okay. 2 is emitter, that's a black. And 3 is yellow, that's a base, that's okay. HFE of 68 and 602 millivolt threshold voltage, forward voltage. Now I swap the transistor. Collector, emitter, and base, and do the same test again. HFE of 67 and 601 millivolt. So we can say with the low test current, I don't know how many milliamps they are flowing, but it's not much. We have an HFE of 67. It's known that with increasing current, HFE increases also. So 80 for higher currents is obviously okay. And so we can say that these two transistors are identical. Before we install the transistors, we have to add some solder on the bottom side, which is not accessible later when we bring them into the PA brick, just to have safe contact. Only a very thin layer, not too much. Then we can add it more easily. And then we have to bend them to the right position. This tab is on the ground. This tab has to be bent up. There are 2 additional contacts in the center. We have this. We have this. And this and this. Oops. And then you have the 4 screws. And later we have the damping resistor, which has to be added here. Which has to be added here, as it was in the PA brick. This will be added later. Now we have what we need. So this emitter, this is added in this way when the transistor is in, but first we have to add the transistor. This has to be bent up. And there was this one. And then this 2-side base and collector also has to be bent up. We have a pattern. Where is it? There's a little bit, you can imagine. This is the old one. I bent it back. This collector, this emitter, the other one which was bent up. And here this is a base. This was a position. Okay. We have to work slowly, carefully. No hurry. Take your time. And then we will see later whether the distance is okay or not. So this is the way the transistors will be installed. The first test was successful. Here we have the emitter. These emitters can be soldered together. The other emitter, 2 base connections, and the collectors are here. That fits. The holes for the screws are in place. Additionally, there were some connections added for the emitter, like this. It's over the emitter from here to here, and from the other side we have the same from here to here, just to make a short. And these 2 lugs here, okay, one seems a little bit broken, is in the center, which is on this screw and then this screw, also to make contact to this bridge here. Okay, we take it out, add some thermal grease, and then install the transistors finally and solder them. The transistors are in place. Then we tighten the screws slowly. Do not over tighten it, of course. And look for the thermal grease. As we can see, it comes out here a little bit. It is squeezed out. You see this white ring. That means the transistor goes onto the heatsink and squeezes out the thermal grease on all sides. That's important. So that's the evidence that you have sufficient and enough thermal grease. Again, not too much. We look for it on all sides of the transistors, that the thermal grease comes out, is squeezed out a little bit. Not too much, only a little bit. This shows that we have sufficient thermal grease. Now it's time to solder. Use a big iron, of course. Bring the brick into a position where you can solder it easily. These tabs are a little bit critical because solder may drop down and this could cause a short. Not a good idea. Okay. Do not overheat it. I think I need a smaller tip for inside soldering. I will swap the tip, but first I do it on the other side. Yes, the base connections are a little bit more easily accessible. Sorry, you can't see it. By the way, the solder station is grounded with this clip. Do not apply too much solder, only a little bit what is needed. Next step is to solder these 2 emitter connections together and solder the 2 lugs to it. So we have emitter, 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 and also ground here and here. This is rather easy with a big iron. Only some drops of this lug is not okay. Okay, now we have a contact. You can imagine that it's important to have the pads here tinned on the inner side so that they squeeze together and have a good contact. Now we are electrically okay, and we do a first DC test before we install the rest of the contacts. I will feed in 12 volt, measure the bias and other things to see whether the brick is okay now, and then we can finalize our work. But in the moment I do not feed in high power, I only use the DC setting. A first test, we have connected 13.8 volt to the bias circuit, not to the final circuit in the moment, only the bias plus 12 volt switched in case of transmit. An analog meter is connected. It's good for demonstration when I make a video. The input voltage is 13 volt. We have full scale 50 volt. So we can check it. Okay. It is 13 volt. And now we check the output of the plus 5 volt. This is a 5 volt regulator. This is input 13 volt. Ground of this output, this is 5 volt. Okay. 10 volt scale 4.9, something that's okay. The bias voltage at the transistor, at the power transistors should be 0.7. 2.5 is full scale. 0.5, 0.6. What does the schematic say? 0.65. 0.65 in case of transmit. Yes, a little bit more. 0.62. Is it? Here we should have, this is the diode for the driver transistor for heat thermal stabilization, should have 0.7. We have 0.7 volt. That's also okay. So we can say the bias circuit is okay. By the way, I've connected here an output damping resistor, 50 ohm. It has 30 watt, just to prevent that the power stage has no load, that it is open. It's not a good idea because we have no protection circuit. The VSWR bridge is not connected with the reverse power protection, so we have to be a little bit careful. An open output for such transistors, when we energize it here with 13 volt, is not a good idea. So we have here the load, it is 30 watt, just to prevent oscillations. Well, we can say the bias circuit is okay for the transistors. Of course, we have no collector voltage. There shouldn't be a voltage. No. And also not no. Small bias. That's okay. By the way, I will check the bias of the driver transistors. What should it be? 0.75. I think this is base. Yes, 0.75. A little bit too less. 6. 0.5. 0.65. A little bit too small. The voltage is a little bit too low. 0.75 should be there. Okay, doesn't matter if the circuit itself is okay, as we have seen. So I do not have any reasons not to continue the work. In the next step, I will energize the PA transistors, the final transistors, with a plus 12 or 13 volt without bias. I only observe the currents flowing. There should be nearly no current flow in because the transmit is not energized. But I will check it. I will increase the voltage on the power supply. You can't see the meter, but I can tell it to you. 6, 7, 8, 9, 11, 13 volt, 13.8 volt, and the current is absolutely 0. I measure 50 volt full scale. We have 13.8 volt connected. Okay, that's it. Same voltage should be present on the collectors. That's it. And on the other side also. That's it. 50 volt full scale. So we have voltage at the transistors, but no current is flowing. That's okay. And now we simulate the transmit relay. Now we mode transmit. I will increase the voltage slowly from 0 to 13.8 volt and have a look at the amps. What's going on? Six volt, 1 amp, 1.3 amp, 4, and at 13 volt we have 1.5 amp. 1.5 amp flowing into the circuit. Base voltage is 0.65 on both sides. That's okay. High frequency I cannot measure, but the current is 1.5 amp flowing into the PA brick. That's a bias current without any signal. We have no signal input here in the pre-driver. That's okay for me. 1.5 or 2 amps, that's what I've seen on other TR7s also. A little bit warm. Yes, but not critical. Yeah, only a little bit. Not much. The dissipated power is approximately 10 watt for both, 5 watt each. We have a good heatsink, so nothing will happen. Okay, that means the DC circuit is okay. We have here again at the collector. Oops, I should go to 50 volt. Yes, on both sides. Emitters, of course, we have nothing. Well, we'll reduce the voltage. Now we can install the rest of the circuit, these brackets, and then bring the PA brick into the transceiver and do the first power test. The brick is ready now. This bridge is also soldered here and here, and in the center it is soldered to the 2 lugs. Damping resistors are again in place. The load resistor, of course, is disconnected. And now I will bring it back into the TR7, connect the plus and minus 13 volt and the switched voltage. There's a separate wire which is connected to here to switch on the bias in case of transmit. In case of receive, the PA brick is not biased, of course. And then we will see what happens. Keep your fingers crossed. And now the moment of truth. The PA brick is in place, it's connected, everything is okay. And we have full output. 7 megahertz, full scale is 200 watt. The ALC needs new alignment, of course. And I have the feeling that this PA now is more sensitive, has more output with the same setting of the carrier. And even on 21 megahertz, where we had a problem, we have nearly 100 watt. And on 28, also 100 watt. Sorry, calibrator is in. On 21, yes. Okay, there is a fold back. The ALC needs new alignment, but in general now we have full output, and the current is 22 amps at 13.8 volt, as it should. So this topic is solved. I will reinstall the PA brick into its right position, and a little bit is loose again. I don't know what this mechanism is with this PTO. I have to look for it. But the main topic is now working. The finals are new and okay. Did you hear this? It was a stone which dropped from my heart. Or to say it with other words, I can wipe the sweat from my forehead. Well, It's the first time for me that I swapped out the finals in a TR7. I will bring it together, and as I have heard, the receiver sensitivity is not okay. I will check it. The PA brick is in place again. Now we have the last topic for this TR7, that's the low sensitivity. I made a check. There is no low sensitivity, and I talked to the owner, asked him what he means. He said, oh yes, could have been, maybe it was an error from my side and so on. And he thought that the S-meter deflection was too low for some signals. There should have been more S-meter deflection. Well, the S-meter of the TR7 is a little bit deaf. For low signals, the S-meter indicates nearly nothing. It's not sufficiently logarithmic. It's more or less a mixture from linear and logarithmic. But I will check the pots for the S-meter and AGC threshold. These are these three pots. A fourth one is for the setting of the gain of the IF chain. I will add a drop of fader loop and hope to clean it and then realign it after it dried out. And now I think I found the problem on this board. When I plugged it in, suddenly I had a problem. And I found that this pot here, it's a sensitivity pot, is bad. This sensitivity pot sets the gain of the IF chain. The original pot is this one. It is a 5 kilo ohm pot. It is used only as a variable resistor, not a pot. And you know the problem when you set such a pot to a value very, very low. In this case, when it's a 5 kilo ohm pot, a value below 100 ohms or so, then it's difficult to set it reliable. The contact jumps around, and maybe the pot itself is bad. So I replaced it by a new one, and now we have only 1 kilo ohm, and this is much better to adjust the sensitivity of the receiver. And now we have a constant S9 for 30 microvolt input as specified. I think that was a problem which the owner has observed. It's always difficult to reproduce faults, intermittent faults, which are there sometimes and sometimes not. But now I think I found it. A general remark to the S-meter of the TR7. The S-meter is a catastrophe. It's not an S-meter, it's not working logarithmic, it's more or less a linear voltmeter. For higher signals, about higher than S5 or so, it is a little bit logarithmic, we can say, but for lower signals it's a linear voltmeter, and the signal drops down rapidly on the S-meter, and weak signals cannot be seen on the S-meter. That's on one side it's not nice. On the other hand, an operator does not operate with the eyes, he operates with his ears and his brain, and not with the eyes. So I think it's not critical. There are some modifications in the net for the S-meter circuit, for the AGC and the S-meter circuit, to improve this behavior a little bit. To swap some resistors against diodes, swap silicon diodes by Schottky diodes, and so to reduce threshold voltages could be done. I didn't do it, I leave it as it is. Such modifications do not make sense in my opinion. It's more or less not necessary. Well, that's it. And now I think we can close this project. Some words about such an old equipment. This transceiver is more than 40 years old. And it has obviously not been used for many, many years. It was stored anywhere in a not very friendly environment. To bring such a unit back to life is possible, yes, of course, but please accept that there will be more problems involved which cannot be seen in the moment. I wouldn't be surprised when I send this unit back to the owner. After 2 weeks I get an email that a new problem arose. Okay, could happen, but yes, I would help again. if possible. Such units are a constant source of work. There are components inside which have a tendency to operate after such a long period of not being used, after a decade, after some tens of hours, 10, 20, 30 hours of operation. This unit was operated now, I would estimate 50 or 100 hours, many hours here in my workshop, and the owner also has checked it, tested it. But still, I am sure there are some time bombs involved, ticking time bombs. I do not know when they explode. And this is not necessarily an electrolytic capacitor. Can be also another component. Transistor, diode may get faulty, bad solder connections on the boards and so on. These old drakes here have not the best quality of the boards and contacts and switches and so on. Anyhow, I will stop this project. It was a very challenging project for me. One of the most challenging projects, or maybe it was the most challenging project, yes, I would say, when I think back last 10 years or so. Anyhow, it was a lot of fun, interesting for me. I hope also for you to see what may happen. But again, do not expect miracles. I can't do miracles. I'm only a human being. I do my best, what I can do. Wait and see what the future will bring. Stay healthy, stay tuned. See you on this channel.